Welcome to the Explainer. If you've ever looked at a circuit diagram and just felt swamped by all the numbers, you are definitely in the right place. Today, we're going to break down the essential language that every single engineer and technician has to master to build, analyze, and, most importantly, troubleshoot circuits. Seriously, this is the bedrock of everything you're going to do.
All right, let's just dive right in with a question that, let's be honest, kind of messes with everyone's head when they're starting out. Picture this. You've got a single circuit, and in that circuit, you have a current that's maybe a few millionths of an amp, and at the same time, a resistor that's millions of ohms. How in the world do you manage numbers at such wildly different scales without getting completely lost? Well, the answer starts with creating a universal language. You can really think of it as the alphabet of measurement. I mean, without this common ground, it would just be total chaos, right? You'd have engineers in one country using one system, another team using something else. Even a simple project would become an absolute nightmare.
And that universal language is the International System of Units, usually just called SI. This table right here shows the fundamental building blocks, the base units. For what we do in electronics, the big ones to focus on are the ampere for current, the second for time, and of course the meter. These are basically our bread and butter. You're going to see these every single day.
Now, you might be thinking, okay, so what? It's just a standard. But this isn't just about being neat. This international agreement has huge real-world consequences. Get this, back in 1999, NASA actually lost its Mars Climate Orbiter. Why? Because one engineering team used metric units while another used imperial units in a critical piece of software. It was a multi-million-dollar mistake. So yeah, the SI system is what stops those kinds of catastrophic mix-ups. It's truly a global language of precision.
Okay, so if the SI units are our alphabet, now we need to talk about the grammar. How do we actually use these units to wrangle those incredibly huge and incredibly tiny numbers that we find all over electronics?
And this is where it can get really messy. I mean, seriously, can you imagine trying to write out 0.0000005 amps on an already crowded schematic? Or 5,600,000 ohms? It's just asking for trouble. One little slip, one extra zero, or one zero too few, and your entire calculation is off by a factor of 10. And poof, your circuit doesn't work. We need a better way.
And that better way is scientific notation. It is such a clever system for taming these wild numbers. All you do is move the decimal point and use a power of 10 to keep track of how far you moved it. Suddenly, any number, no matter how big or small, becomes clean and compact. Take 85,000. It just becomes a much more civilized 8.5 times 10 to the fourth. It's clean, it's simple, and it's way harder to mess up. But, engineers, we like to be even more efficient. We've kind of developed our own professional dialect, a shorthand that's even better for the specific kinds of numbers we deal with every day.
And here it is. This is engineering notation. Just look at how slick this is. Instead of writing out times 10 to the something, we just use a simple prefix. So, 5.6 times 10 to the third ohms becomes 5.6 kiloohms, or 5.6 KO. A K for kilo, a little m for milli, a capital M for mega. This is the language you see on schematics and data sheets. You've got to speak this fluently.
So what's the secret sauce here? What makes engineering notation different? It's all about the multiples of 3. See, we only use exponents like 3, 6, 9, or on the small side, -3, -6, and so on. And why do we do that? Because those powers of 10 map perfectly to the standard metric prefixes that components actually use. It's a system designed for maximum practical use out in the real world.
And once you get this, this is where you really start to feel like you know what you're doing. With a solid grip on these prefixes, you can just effortlessly glide between different scales of measurement, going from milliamps to microamps, or from kiloohms to megaohms. It'll just become second nature.
Okay, these prefixes are your new best friends. Seriously, you need to know them inside and out. Being able to instantly see kilo and think 1,000, or see micro and think a millionth, that's what's going to make you a faster, more confident, and more efficient engineer.
All right, deep breath. So far, we've been living in the clean, perfect world of theory. But now we have to step out of the textbook and into the messy reality of the lab. Because the numbers you get from an actual measurement, well, they're a whole different animal.
This quote really gets to the heart of a huge issue. When you measure a resistor and your multimeter reads 12,100 ohms, what does that number actually mean? How precise is it? Is it exactly 12,100? Or is it just somewhere around there? That kind of ambiguity is a big problem, which is why we have to talk about precision. The best way to think about this is that significant digits are like a measure of trust. They tell you exactly how much confidence you can have in a number. A cheap multimeter might only give you 2 or 3 significant digits, but a high-end benchtop meter might give you 5 or 6. And in engineering, that difference in trust can be the difference between a project working and a project failing.
When it comes to significant digits, zeros are the troublemakers. They're a little tricky, but these rules make it simple. A zero squished in the middle, like in 507 volts, always significant. Zeros out front, like in 0.002 amps, never significant. It's the zeros at the end that you gotta watch. A number like 560, we don't know if that last zero is significant. But if you see 5.60 with a decimal point, that tells you it is. That tiny dot carries a whole lot of meaning.
And this is where it all comes full circle. Our friend, engineering notation, comes to the rescue again. Because when you write that resistance as 12.10 kiloohms, you're not just making the number easier to read. You are making a clear, unambiguous statement about its precision. You are telling the world, I measured this and I'm confident in it to 4 significant digits. It's simple, it's elegant, and it's how professionals communicate.
So what's the big takeaway here? This is not just about passing a test. This is about learning how to be a detective. When you're troubleshooting a circuit, the tiniest difference between the number you expect to see and the number you actually measure, that can be the one clue that cracks the entire case. Mastering this language of numbers and precision is your first real step toward becoming an expert problem solver.